Still under the review process that we are doing, we are almost done with the aquifer properties, not all. We just talked about the storage properties. If you remember, we classified the aquifer properties into three, right? We have the storage properties, and we have what? The hydraulic properties, isn't it? And then we have others. So under the storage properties, that is when we define the specific yield, retention, storage coefficient, and specific storage. Before we move to the hydraulic properties, where we will talk about the hydraulic conductivity, the permeability, hydraulic conductivity, permeability, yes. These are the transmission or the hydraulics properties or the transmission properties. We need to take some review before we move into that. And this review will cover what is called vectors. What we did for the PhD guys, we just started with the review, even before starting anything. Because in that case, the aspect of the modeling will be much deeper than this, and we'll go straight into vectors more often than not. So that's why in that case, we just started with the vector review. But here, after this review is when we will start to introduce the vector aspect of the course. So we need to go back and review basically what we did in Math 106. Okay? Back to vector algebra, Math 106. For those of you that passed through, that did your undergraduate here, you know what is Math 106, isn't it? For those that did not pass through here, wherever you graduated from, you must have done vector algebra. Yes. Who and who didn't, pass through here? Did your undergraduate elsewhere? Okay, I have 4. But have you done vector algebra during your undergrad, right? Okay, good. So we are, all safe. But nevertheless, we are still going to review the same vector algebra which you did, laying emphasis on certain things that will affect us immediately after the review. Of course, I always say, I will not just assume that all your knowledge about vector algebra is still intact up till now. Okay? Over the passage of time, depending on how much you use it, a lot of the concept will probably, you may forget, isn't it? So we'll review those same concepts here. And then, like I said, immediately after that, because we are going to apply them. So I wouldn't be starting, to write some things and you'll, what is this, what is that? And I will just maybe tell you, haven't you done it? Yeah, you have done it, but probably have forgotten. So we'll assume that you did nothing about vectors before. We'll review it from the beginning till where I feel, it's comfortable for us to move on. Okay, then we'll build on that. Okay, so this is going to be review number 1. Okay, about vectors and scalars. Scalars and vectors. We'll define scalars and vectors and explain operations, vector operations such as multiplication and division of a vector by a scalar, and vector addition, subtraction, and resolution of a vector. Scalar quantities. What are scalar quantities? Very simple, isn't it? SS1 physics, right? Yeah. Go ahead.
A quantity that has magnitude, no direction.
Has only magnitude, isn't it? No direction. And when we say magnitude, what do you mean by magnitude? Yes? Yeah. What do you mean by magnitude? Like I said, in modeling, we have to understand and know everything, isn't it? No matter how simple it appears, no matter how used to it we are, isn't it? We are used to calling magnitude, but what is that magnitude? Don't tell me you don't know what is magnitude. Huh? Please put it in a way that we'll understand. Don't worry. Just put it in a way that we will understand. any way that is understandable by us is welcome. What is magnitude? Someone defines scalar as a quantity which has only magnitude. And now I'm now as underlining that magnitude. So what is that magnitude? Quantity, size. How do we define it? How, either mathematically or whatever? Hmm? And what? He said it has a value. Someone say quantity. Someone say it has a value. Saying the same thing, isn't it? But he said it has a value. A value meaning numerical value, right?
Numericals.
So, and what?
And units.
And unit. And unit. Okay? And unit. A magnitude has a numerical value and unit. Unit is very important because in science, in engineering, we don't forgive. Like now this calculation which you did, at the end you write the unit of what? Compressibility, which is meter square per Newton. If you don't do that, even if you get the value correct, the magnitude correct, the numerical value correct, we will subtract something. Because without units, quantities wouldn't have been differentiated. The only thing that differentiates one quantity from another is what? The unit. 10 kilometer, 10 meter, 10 Newton. The magnitude is the same, but it's the unit that tells you this is a force, this is a distance. Even the distance, you have kilometer, meter, feet, and what have you, isn't it? So unit is very, very important. And not only unit, but the correct unit. That's why even in your calculation, like I said, if you have all the steps correct, the final answer you use a wrong unit, there will be deduction there. Okay? Because we don't forgive when you write wrong units. No way. You have to write the correct unit. Okay? And that's what constitutes magnitude. Okay? A scalar is a quantity that has only magnitude, either positive or negative. Either positive or negative. That is very important. Okay? Either positive or negative. For example, give me one example of. Okay, I will not ask you. You. One example of a scalar quantity. Volume. Oh, he has already seen it. Yes, you. Mass. He has already seen it. Give me one again. Time. Okay. So all these are scalar quantities in the sense that you define them with magnitude only. 10 seconds, 10 meters. Is it? Yeah. Yeah. Distance. Because we have distance and displacement, which are different. Okay? Distance is a scalar quantity. Okay? And we have mass. Yeah. Mass is also a scalar quantity. Okay? Length. And they are indicated using italic, okay, by letters in italic type, such as, now vector quantities. What are vector quantities? Yes. It has both magnitude and direction, okay? Magnitude and direction. Vector quantity has both magnitude and direction. Example, acceleration, velocity, force, displacement, speed. Speed, right? No. Okay. Weight, yeah, which is also a force. All these are vector quantities, okay? Position, force, and moment, okay? All these are vector quantities, and they are indicated in bold. That's in print. You can type in bold, isn't it? But in writing, you indicate using a small arrow to show that it has direction, isn't it? That is when writing using your hand, isn't it? Write the letter and then indicate it that, okay, this is a vector quantity. While in print, you can type in bold. It is written in bold. We are going to expatiate more on the vector. The magnitude of a vector is always a positive quantity. The magnitude of a scalar can be positive or negative, isn't it? That of a vector is always a positive quantity and is symbolized as, still in bold but tilted in italic, or we use the modulus, isn't it? That's the magnitude of a vector quantity. Let's say 10 Newton. That's the magnitude of a vector quantity, isn't it? A force, right? Yes.
How about deceleration?
How about,
Deceleration.
we are going to explain that. Okay? It is always a positive quantity. We are going to explain that in the few slides to come. A vector, now representation, vector representation. A vector is represented graphically by an arrow, which is used to define its magnitude. The length of the arrow defines the magnitude, and then the direction is defined by the angle between a reference axis and the arrow's line of action. That defines the direction. And the third one is the sense, which is defined by the arrowhead. The arrowhead is called the sense. Okay? For this vector, you have the length from here, from tail to head, defines the magnitude. The direction defines by the inclination, angle of inclination with a reference axis. In this case, the x-axis, isn't it? This is the direction. And this is the sense, the arrowhead. Okay? If you define this into units, from here to here, 1 unit. So this has magnitude of 4 units and a direction of 20 degrees measured counterclockwise from the horizontal axis. The direction, of course, can be measured from the vertical axis. Okay? It mustn't always be with respect to the horizontal axis, but it has to be with reference, using a reference axis. Okay? And then the sense, which is upward and to the right. And point O is called the tail of the vector, and P is called the tip or head of the vector. Now, vector operations, multiplication and division of a vector by a scalar. When you multiply a vector and a scalar, A, it becomes AA. We'll demonstrate it, and the magnitude is given by this. And the sense of the vector, the product of the scalar and the vector, will be the same if the scalar is positive, and will be reversed if the scalar is negative. Yeah, will be opposite if the scalar is negative. We are going to demonstrate this. Some graphical in this vector A, when multiplied by -1, which is negative, you see, it changes the sense from this to that, isn't it? Okay, it changes the sense when multiplied by negative scalar. If it is positive, the magnitude only increases, it doubles. When dividing, it reduces, isn't it? And when you multiply by negative scalar, it changes the sense, isn't it? Vector addition. When you add two vectors, they form resultant. Resultant means just summation. R equals A plus B, but all these are in vector quantities, meaning this is R, this is A plus B. R is the resultant, which is just summing A and B in vector form, meaning A and B must be in vector form. Using the Phelan methods, more often than not, if A and B are given in vector form, A and B in vector form, then we will have no trouble, isn't it? To find the resultant, we just add them up, and then we have the resultant vector, right? But more often than not, the vectors are not given in vector form. We only have the magnitude of the vectors, like 10 Newton, 10 kilometer, be it displacement or what, isn't it? In that case, we need to devise a means by which we get the resultant vector. Okay? So we need to devise another mathematical method by which we can get the resultant vector. Of course, if the vectors are given in vector form, very simple, straightforward. But life is more difficult than that. Okay? So, and that's what takes us to the next, which is the resolution method. How do we now get the resultant vector? We can use the parallelogram law and the triangle construction. The first thing we do is the parallelogram law. And then from there we move to the triangle construction. What do we do? If you have any two given vectors, we construct a parallelogram around them. Oh, but as usual, that takes us back to some basics. What is a parallelogram? What is a triangle? What are their properties? How many triangles do we have? What are their properties? Now this is JS1 primary school mathematics, right? So let's start with parallelogram. What is a parallelogram? Yes. Very simple, straightforward, yet you have to tell me. Yes? You want to say something? Okay. Okay.
Is a polygon,
Okay.
has 4 sides,
Okay.
and each of the pairs are parallel. That means it has 4 sides.
Opposite sides
Opposite sides
are parallel. Good. So opposite sides are parallel. Okay. Any addition or subtraction? Yes.
Parallel, the sides are parallel. Two opposite sides are parallel, and the diagonal differs. One is bigger than the other.
And then the diagonal.
It depends. It depends.
The diagonal.
Because for rectangle is a parallelogram, yet the diagonals are equal.
No, they are not equal. At times they are not.
What about the size? Are the sides the same? The opposite sides, are they equal?
Yes.
Opposite sides are not equal.
They are equal. The opposite sides are equal.
Are always equal, isn't it?
Yes.
And parallel.
The diagonal as well always divides the parallelogram into two.
You guys, because that was what we did in the class, so don't say anything. So the diagonals always divide the parallelogram into 2 equal parts, equal triangles. But does it divide the angles into 2?
Yes, it does. It does.
No, it doesn't. Yes. The diagonal doesn't divide the angle into 2 equal parts, into 2 equal angles. Because this is very important. You will see the implication of this when we will solve some problem. Okay. What else? What about the sum of angle in a parallelogram? 360. What about the sum of opposite angles in a parallelogram? Does it add up to anything? The sum of opposite angles in a parallelogram. You know, all these properties are very important, but I don't want to write, but at least when we talk, if you feel you want to write it down, you can write it down. But the most important thing is that it has to be retained, no matter what. Whether you write it down or you don't, you have to always remember them at all times. So, what about the sum of the opposite angles? 90? 180? No. They are neither complementary nor supplementary. Okay? But the sum of angles inside the parallelogram is equal to 360. Now, I think we have reviewed most of the properties, all the important properties for a parallelogram. Now, let's come down.
But we add that none of the internal angle is right angle.
No, we can't add this because what about a rectangle? All the internal angles are right angle. It's also a parallelogram, a special case in which all the internal angles are equal and equal to 90. Yeah. So that shouldn't be a property of a parallelogram. Now let's move to triangle. The plane shape which you are most familiar with. Triangle. How many triangles do we have? What are their properties? Yes. Triangle.
Some of the interior angles is
180, good. Yes. How many types? Let's go to types now. You are talking about the angle, not triangle now. I said types of triangle, not types of angles. What? Equilateral has all the sides equal. Isosceles has what? 2 sides equal, and 2 opposite angles are equal. Yes? Yeah, base angles. Yeah, they are opposite. And what? Right angle triangle. And what? Scaling triangle, in which none of the angles or sides are equal. For right angle triangle, if I want to find the sides or the angles, what do I use? What mathematical tool do I use? Formulation. Yeah, that's about the side. What about the angle? Sine rule. Sokatwa. Which one? Sine rule or sokatwa? Can't I use the sine rule?
You can use.
Both. But preferably for right angle triangle, the simplest way is to use sokatwa, isn't it? But still sine or cosine rule are applicable because later they will reduce to sokatwa when applied to right angle. What about the scaling triangle? Scaling triangle? Cosine rule? What about the sine rule? Only cosine rule? What about sokatwa? What about sokatwa for scaling triangle? It can also be applied. It cannot. Why? Why no? I say scaling triangle. Has none of the sides equal? None of the angles equal. Scaling triangle. Why no? Why? So sokatwa is only for a right angle triangle. Did you take note? Okay. So, what about the sine rule? Can I apply it here? Cosine rule, isn't it? What about the area of a scaling triangle? Although this may not apply, okay, we may not use it, but just let's see. How can I find the area of a scaling triangle? What?
You divide the
When I have only the sides, we use Pythagoras. What is Hero's formula? What is Hero's formula?
There is serious formula, but I can't recall it.
What is Hero's formula? Is there where?
It says you take half of it.
No.
No, that's not it.
Square root of the semi-perimeter minus semi-perimeter minus A.
What is semi-perimeter?
Add of A
Divided by 2. Get your divided by 2.
Is it 2 or 3? And then the area?
S into minus A. S minus C. S minus C.
If you have kids in the primary school, sometimes they will embarrass you in that case. When the teacher gives them something like this. So, what? What? Is this not primary school geometry? Okay, junior. Let's say junior. Okay? But we have to remember all this. And when I say remember, I mean at all times. At all times. At all times. Okay? You can see, probably some of you have never thought you'll come across this again. But you will keep on coming across them. And sometimes you'll come across something that you may never expect or have never imagined to come across it. Okay? So all these small, things that we take for granted, no. Because see, today we talk about Le Chatelet's principle, although we are not doing chemistry. But that helps us to explain certain processes here. Okay? And that happens all the time. Yes. Yeah. You told me to. You told me to, right? Okay, now we will not deal with area here more often than not, but the other, plain geometry. Haven't dealt with parallelogram, triangle, Now, plane geometry. Huh? Keep on telling me all the rules for plane geometry. SS1 mathematics. Plane geometry. Hmm? Oh. No. Plane geometry, when you have straight lines. And telling me about the angles. These angles. This angle. Okay. Go ahead. Tell me about them.
I'll go about a point distinction.
Alternate angles are equal, isn't it? Corresponding angles are equal. Vertically opposite angles are equal. Sum of angles on a straight line is equal to 180. Okay, good. All these are going to be utilized, okay? Okay. Now, don't forget our topic. We are trying to learn how to perform vector operations, where we say that when you sum vectors up, two vectors, they form resultant vector, okay? When they're in vector form, it becomes straightforward. Simple addition, okay? But like I said, more often than not, you don't find it that way. You find the vectors being represented in magnitude only. So in that case, you need to devise a means by which you find the resultant vector. And one of them is to apply the parallelogram law and the triangle construction. How do you apply the parallelogram law? When you have two given vectors, A and B, you can join them, they form the sides of a parallelogram and complete the parallelogram, okay? And the diagonal forms the resultant, okay? You have A and B forming the sides of a parallelogram, so you project it. Meaning this is equal to this, isn't it? This is equal to that. And the diagonal forms the resultant, okay? You can see, you join the vectors head to head. Sorry, tail to tail. And then the diagonal also joins the vector from tail, okay? And then it forms the resultant. This is the parallelogram law. We mentioned that the diagonal divides the parallelogram into two equal triangles. So you now apply the triangle construction. You take any one of them, any one of the triangle. But you can see the diagonal, sorry, the resultant. Now, if you see very well, this vector, this is equal to this. So that's why we just put A here. The resultant here is always touching the tail of one vector, tail to tail, and the other one head to head. This is very important. Because, okay, let me ask you this. The resultant vector, is it always going to be longer than all the other vectors?
Depends on direction of the vector.
Not always? So what is the condition for me to identify a resultant vector when I have a triangle containing three vectors and one of them is a resultant vector? How do I identify it? Is it by looking at the one that is the longest? Is it like that? Or what?
Look at where it is, the origin, where it's starting from.
And what is that? What is the condition?
The condition,
The tail of
touches the tail of one.
Like this one, this is the resultant vector. What about this one? Okay, let me. No matter what it, okay. Who can identify the resultant vector from this one? C, B. Any other option? C?
No, it's B.
Because the condition for identifying the resultant, it has to be tail to tail, head to head. So it is not that you look at the one with the longest side and just say, okay, this must be the resultant. No. This is the condition. Okay? Which I forgot to mention in your class, but probably I will mention that the next time. Okay? All right. Now, when you isolate this, you now apply your plane geometry to find the angles inside the triangle as much as possible. And then you apply either spiral or cosiral to find the side, which is like in this case, the resultant. Okay? We'll take some few examples and demonstrate how to use that. But you can see that we start from the parallelogram, construction of a parallelogram, and then we take out a triangle out, isn't it? And then analyze it using the simple trigonometry that we are all aware. Okay? And if they are collinear, if the two vectors are collinear, the resultant is just simply, this plus that. Very simple and straightforward. But like I said, you can either you can use any of the triangles because they are equal. You can choose to use this or that. Okay? Whichever one you choose to use, you will arrive at the same answer. Okay? Now, vector subtraction. Vectors A and B may be subtracted to form a resultant vector. A minus B, it will be just A plus minus B. And then using the following methods, minus B will be what? We change the sense, isn't it? And then the resultant will be the same thing, A plus minus B, okay? Which we can use any of the triangles. A vector may be resolved into two components, having known lines of action by using the parallelogram law. Now we are going to the reverse. Initially we have two vectors and resultant. And now when we have resultant, it has two components. It can be resolved into two components having known lines of action by using the same parallelogram law. Okay, if you have a vector R, it can be resolved along B and along A. Okay, much the same way as when you have two vectors. So this vector is just like the summation of the vectors along its component, the same way we did before. Okay, so it has component along A and along B. A and B could be the X and Y axis. Okay, although here they are not rectangular, so generalizing, but in practice, we have the rectangular coordinates, so it will be the components along the X and Y axis. Oh, this one. Material. No. Okay. Who can tell me the answer to this? Multiplication of a vector by a scalar. Understand it very well, okay? Digest it first. Multiplication of a vector by a scalar will never change the vectors A, magnitude, B, sense, and C, direction. What is the answer to this? Very simple. Sense. Multiplication of a vector by a scalar will never change the vector's sense, direction, sense. Direction. So no matter, some are for sense, some are for direction. Sense. Let me see. Those for sense. That multiplication of a vector by a scalar will never change the vector's sense. 1, 2, 3, 4, 5, 6, 7. Okay. 8. 9. 10. Oh. Direction now. 1, 2, 3, 4. Only 4. 4, right? Magnitude. Okay, now let's analyze all the cases and see who is right and who is, coming to the right, or who has to be pushed to the right path. We did all the operations. Oh, here we have a vector, right? We multiply it with a scalar. Here we multiply with plus 2, right? It changes the vector's magnitude. Here we multiply with a negative scalar, minus 1. It changes the vector's what? Sense. So the sense changes, right? Here we divide by a scalar. It changes the vector's magnitude. Is the direction affected? is unaffected.
The direction is not.
The direction, it doesn't change when you multiply a vector with any scalar. It's only the things that is affected, which is the arrowhead, isn't it? And we say that a vector, the magnitude of a vector is always positive. Yeah. You see here, you may say, why this negative? Yes. We say the magnitude is always positive. The negative is saying that it's opposite to the direction of A. Simple. Yeah, it's the same. Like positive x-axis and negative y-axis, and negative x-axis. Simple. What do you mean by specific capacity? The specific storage, but the magnitude will always remain positive. We are going to also do more on this. The yield. That is the specific yield. No, these are the most important aquifer parameters that will affect our modeling process. Of course, there are others, but these are the most important storage aquifer parameters that will affect our modeling process. And you are going to see when we start the modeling proper. Okay, we need to know them, we need to have their values and then input them in our model. Okay? Any other question? So in the absence of any other question, we call it a day. See you next week.